Thanks. I'm excited today to talk to you about a micro framework we built at Stitchfix for creating data frames. So two things to keep in mind for the next 8 minutes that I'll hopefully kind of convince you of. The first is what I'm talking about. Hamilton is a new paradigm for creating data frames from a user perspective. The second is Hamilton enables data scientists to focus on functions rather than glue code. So to start, I'm going to talk about backstory of why we created Hamilton, then talk about Hamilton itself, our experience using it, and then future directions. So backstory, there's a forecasting, estimation, demand team, or FED for short. They're a team of data scientists at Stitchfix who help create forecasts for the business that then the business uses to make operational decisions. So for instance, what should our staffing levels be at the warehouse? It's also one of the oldest teams at Stitchfix, so their code base has been around a while. Their basic workflow is the following. They take business actuals, so signups, marketing spend. They create a featureized data frame from it. They fit a bunch of time series models on that, which predict the future, which then output a forecast that the business uses to make decisions. What was happening was this pipeline was on fire for them. And given the operational nature of their role in that they need to help the business make decisions, when this was happening, they were understandably quite stressed. What ended up happening was the biggest problem that they were encountering was in creating and managing this featureized data frame. And so this is the focus of the talk and where Hamilton solves their problem. Specifically, what's wrong? What was troublesome about this data frame? Well, this data frame is essentially thousands of columns wide, but maybe on the order of like 1,000 rows kind of deep. The point here is it's not big data, so it all fits on a single machine, or Amazon has big enough machines for it. The second is why there's so many columns. Well, in their featureization process, they're given some initial data column. They're creating new columns from inputs of other columns. So one column can be an input to another column, which can be an input to another column, etc. And so they were having trouble managing this type of dependency chain. Why was that the case? Well, here I have some code. For those of you who know pandas, this should look pretty normal, like nothing egregious. You're probably like, this looks like normal pandas code. And I want to tell you, if you scale this to 1,000 columns in a growing team, you're going to run into issues. Specifically, like if you scale this code, like what happens is you have a lot of different like heterogeneity in terms of how people define functions. So they're trying to create add things to a data frame. So do you pass in the entire data frame to the function or just the columns? Do you modify it in the function or outside of it? And then this being data frames, people are doing a lot of inline data frame manipulations. But the overarching kind of problem with this is like you need to really understand how the code is ordered to really understand what depends on what. What this ends up resulting in the code base is that unit testing is very difficult, especially with inline data frame manipulations, or at least it's very inconsistent. Similarly with documentation. As the code base grew, onboarding and debugging kind of grew, became more costly just because it's really hard to understand what depends on in what ordering was this executed, etc. In terms of the backstory summary, so the two things to take away is the code for featureization was causing them headaches, and the other is that data all fits in memory. So what is Hamilton? Hamilton mechanically is data scientists write code that gets translated into a DAG, which then gets translated into a data frame. Specifically, the data scientists write code that does not manipulate any data frame whatsoever, which then Hamilton takes over, which is code owned by platform. And then the data scientists then tell the library like, hey, I want a data frame, and then they get one. As I mentioned, I think Hamilton's a new paradigm for them in terms of creating a data frame, and that's because they write functions. They don't manipulate a data frame directly. Here I have an example that we kind of translate to. So I'm trying to create, say, column C from summing column A and column B. With Hamilton, what we would do is that we'd write a function where the function name corresponds to the output column we want to create. And the input parameters end up being the input columns that are required for that function. From that, we can go then build a DAG. Along the way, we can use Python type hints to statically check this DAG before executing any code. And then documentation is natural just because we can reuse the function doc. You might be wondering, okay, so how do we go from this function to a DAG? Well, pretty easy. Python has a great module called the inspect module, which allows you to kind of introspect code. So we make heavy use of that. And then it's just building nodes and edges and graph theory 101 to create a DAG, and then traverse it to create a data frame. You might be wondering, why is it called Hamilton? Well, as one of the hardest problems in computer science, naming things is hard. When we were coming up with this project, we were thinking about what associations do we have with the Fed? I had recently gone to see Hamilton, the musical, and I was thinking, well, Alexander Hamilton is the father of the Fed, or the Federal Reserve. And the Fed team, in a sense, kind of models the business mechanics. So, an analogy to, say, quantum mechanics, and there are Hamiltonian concepts there. And then we're also doing some basic graph theory, so which also has Hamiltonian things in it, so apropos Hamilton. Okay, so what does this actual code look like? You might be wondering, what are the data scientists actually writing? So here I've actually translated the data frame code that I showed previously, but into Hamilton functions. These functions will live in some sort of module, say myfunctions.py. And the main takeaway here is that the function names correspond to output columns in the data frame, and the input parameters to these functions just correspond to input column dependencies. So to go from that, you're then like, okay, so how do they create the DAG? All right, you need to write then a little script. The data scientist writes a little script to orchestrate things. So specifically, they need to initialize some data or configuration. So they need to handle that themselves. But then they then need to specify what Python module to crawl to create and kind of get these functions from. They create a driver which kind of merges those two things together to create an execution plan. With Hamilton, the nice thing is that if they only want a subset of columns, they can just specify that. Whereas in the old way, you had to get any columns, you had to run everything. And lastly, then with that, they just kind of call execute and they get a data frame. One of the nice things we added is, they can also visualize what's actually being executed, so they can actually understand what's going on under the hood. So what's the result been? This has been in production for over a year and a half, and I think it's been a pretty resounding success. And that's in large part to getting data scientists to kind of reframe and rethink and write these kind of very specific functions. Specifically, unit testing becomes standard and is applicable to the entire code base. We actually found a bunch of bugs in migration that we wouldn't have found otherwise. Documentation is also super easy and natural because you can use the function doc, and then you can use tools like Sphinx to kind of expose it for wider coverage, for wider readership. Visualization comes naturally because we can build a DAG. It's very easy then to visualize. Onboarding therefore becomes simpler because we can give people visual means to understand the code, but then it's also very clear and concise as to how this column was created. Similarly with debugging, since we can specify dependencies, it's very, and along with visualization, it's very easy to if there's an issue, isolate it very quickly, and even be test driven with fixing it. Since Hamilton does result in a slight increase in kind of lines of code, just because if you're taking a single line data frame incantation and turning it into a function, you're going to increase the amount that you write. So we do have syntactic sugar to keep things dry. Specifically, we use Python decorators for that. And then what this ends up resulting is data scientists don't have to worry about glue code. They can just focus on writing functions which enable better featurization, which enable better models. And the glue code, therefore, platform and my team kind of owns that. In terms of, here's a quote from a data scientist on their experience kind of onboarding onto the system. The TLDR is, basically previously their experience with onboarding was, code bases are hard to understand. It's not obvious where things are used and it's very easy to break things. But with Hamilton, essentially there's no prior domain knowledge required to ramp up because dependencies are very clearly specified, functions are simple and concise, and it's therefore hard to break things. So future. So we have a DAG. It runs on a single core, single machine, but there are tools and libraries that could potentially enable us to easily scale this out. So for instance, Ray, as you've seen before earlier, or even on Spark, or even compiling to Metaflow. We're interested in open sourcing this. Do hit me up if you're interested. We currently support Python 3.6 and 3.7, but curious to hear if other people would be interested in using this. We can extend this to general featurization problems, especially if we can make it work in distributed settings. So we're looking at ways to take this more mainstream. But Hamilton isn't limited to creating data frames. It can actually be extended to be anything that can be union or merged together. So that's my lightning talk. I talked at you for a bit. Happy to take questions. Thanks.